Good afternoon. This is your Chem 122 video lecture to be watched on or before MLK Day, January 2021, picking up with where we left off in the lecture today. Just real quick review. Remember, we said that the orientation, the shape, the size, and the bond angles that we find in methane, CH4, are not consistent with the atomic orbitals on carbon being associated with a 2s or a 2p kind of atomic orbital. We said that the molecule has to undergo, or the atoms have to undergo some kind of change to form bonding structures that are correct with what we actually find in the molecule. So the bonding orbitals that are on carbon are not the atomic s and p carbon orbitals. They're a different kind of orbital. We say these guys are hybridized, meaning an s orbital combines with the p types and forms a different kind of bonding orbital. So we have hybridization, and we find that we have 4 sp3 hybridized orbitals. We have a combination of an s, one s type, not a 2s, but one s type of orbital, compared with 3 p-type orbitals. Not 3p orbitals, 3 p-type orbitals, to form what we call sp3 hybridized orbitals. Each sp3 hybridized orbital is identical to all the others, giving us the identical bond strengths, giving us the identical bond lengths, and those specific angles and orientations such that they match the tetrahedral bond angles and molecular geometry that we see in methane. So we have one orbital that sticks to the back left corner, one orbital that sticks to the very front corner, one that sticks to the right corner, and one that sticks up. Where these points are, where the orbitals go to almost zero, that's where the carbon atom is. So the carbon atom is located here in this orbital, there in that orbital, here in this orbital, and here with this orbital, giving us the, when we superimpose all 3 of these on top of one another, this gets us to the 109.5 bond angles that we see in methane. Figure on the slide is figure 10.8 from the bottom of page 432. It shows the formation of 4 covalent bonds between the sp3 hybridized orbitals on the carbon and the 1s orbitals on the hydrogen. This gives us the tetrahedral shape and the bond angle of 109.5. Another example of sp3 hybridization is found in ammonia. The arrangement of 4 electrons is, again, an electronic geometry that is tetrahedral, so that we make the assumption that the orbitals are much like those that are present in carbon. Remember that the molecular shape of ammonia is trigonopyramidal, HHH. All these 3 hydrogens are in one plane, but the nitrogen sits above the plane that's contained in that contains the hydrogen. So the nitrogen sits above it. We have an sp3 hybridized orbital here, an sp3 hybridized orbital here, and an sp3 hybridized orbital there. And then we have an sp3 hybridized orbital here that already has 2 electrons. Well, where do we get that? Well, let's draw the Lewis dot structure of ammonia. Remembering Lewis dot, NH3. What's valence number of valence electrons for nitrogen? 5. How many hydrogen? 1. How many hydrogens total? 3. So 5 plus 3 is 8. We have 8 valence electrons. Center atom, nitrogen. How many electrons does the center atom want? 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. So this orbital contains 1 electron from the nitrogen. This orbital contains 1 electron from the nitrogen. This orbital contains 1 electron from the nitrogen. This orbital contains 2 electrons that were already accounted for right there. The other electron here comes from the hydrogen. The other electron here comes from the hydrogen. The other electron here comes from the hydrogen. This nitrogen is sp3 hybridized. The nitrogen doesn't have 4 things bonded to it. It only has 3. But this electron pair goes into an sp3 hybridized orbital. I don't know, I can't really tell if it accurately depicts it, but the size of this orbital should be slightly bigger than the size of this sp3 orbital, than that one and that one, because of the presence of the 2 electrons. Since this orbital is slightly bigger, these angles between this, and this are all smaller, about 107. So this gives us an understanding of why ammonia forms the compounds that it does. This gives us the correct bond angle that we see of less than 109.5. Now, we can have a number of other combinations of s and p orbitals. There's not just sp3. The molecule beryllium chloride, BeCl2, 4 valence electrons from beryllium, 12 from chlorine, 6 from 1 chlorine, 2 chlorines is 12. 16 valence electrons. Be 1, 2, 3, 4. We've taken care of 4 valence electrons. We have 12 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So finishing out the number of valence electrons puts them around, completes the octets around the chlorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Beryllium chloride is a linear molecule. When we look at the bonding structure from the valence shell electron repair repulsion theory. Valence shell electron pair repulsion theory, VSEPR. Well, how can we get a linear molecule using hybridized orbitals? Well, what if we only use one s and one p-type orbital? It gets what is known as sp hybridization. We have an orbital that goes to the right and an orbital goes to the left. That would give us a linear molecule. So we have an sp hybridized orbital here and an sp hybridized orbital on the beryllium. Beryllium's electron configuration: 4 electrons, 1s2, 2s2, right there. empty 2p orbitals. If we promote one electron up from the 2s into the 2p, we only have electrons in the s and p orbitals. Therefore, the only ones that we could mix together that would find any chance of bonding would be an sp kind of orbital situation. So we have sp, two of them, hybridization, HYB, BRID, hybridization from an 2s2p to an sp hybridized system. Each of equal energy, each having the right bond angles, the right bond lengths, the right bond strengths for what we actually see when we look at beryllium chloride. For chlorine, how many valence electrons does chlorine have? 7. How many is it looking to gain? 1. So the 8th electron that this chlorine wants comes from the beryllium. I'm just showing these electrons as up or down so we can get that up-down spin pair that we saw with the SEPR. I'm not saying necessarily that either one of those is one of those spin pairs, is exactly that spin rotation, either up or down. I'm just saying they exist in this orbital by being spin paired. So therefore we have one electron in this sp and one electron in that chlorine. Chlorine has 1, 2, 3, 4, 5, 6, 7. This chlorine has 1, 2, 3, 4, 5, 6, 7. The other electron that chlorine wants comes from the electron from this sp orbital on your beryllium. The electron that this chlorine wants comes from the sp orbital from that beryllium. The chlorine orbital here is not hybridized. This is a unhybridized 3p orbital on chlorine. Why? If we look at the electron configuration of chlorine, 1s, 2s, 2p, 3s, 3p, it has completely filled the 2 shell. And it has only one space available for an electron in the chlorine. It's in the 3p orbital. So this is an unhybridized 3p chlorine atomic orbital, but the orbital on the beryllium is hybridized. Well, we've seen that center atoms can be sp3 hybridized. There's sp hybridization, which is what was shown to you for the beryllium chloride. We can form what are known as sp2 hybridized orbitals. So we hybridize an s and 2p type orbitals. BF3, boron trifluoride. Molecule is trigonoplanar. Boron has a valence shell electron configuration of 1s2, 2s1. 1s, 2s, 2p. There, boron has 5 valence electrons. One s2, 2s2, 2p1, 5 valence electrons. If we promote an electron from an s orbital to a p orbital, and we hybridize these guys, we're combining two p types with an s type, giving us an sp2 hybridized orbital. These orbitals can exist at the 3 corner vertexes of a triangle. Again, where these slim down to almost nothing, that's where your boron is. Electron density is to this point of the vertex, this vertex, and that vertex. Everything lies in the same plane. The bond angles are 120 degrees. This is consistent with what we actually see in the molecule of BF3. So here's where we see BF3. This is an sp2, sp2, sp2 hybridized orbital. This fluorine is in row 2. This is a unhybridized 2p. So by mixing the s and the p orbitals, we can get into sp2 hybridized orbitals, which explains the bond lengths, the bond strengths, and the bond angles that we see when we actually look at the BF3 molecule here. So we've covered sp, sp2, and sp3. There are more hybrid orbitals than just the s and p combinations. We've talked about compounds that have expanded orbitals, expanded octets. These are usually atoms that have the center element in the third row. So like aluminum, silicon, phosphorus, sulfur, chlorine, if those are a center element, they have empty, vacant d orbitals that are available to stick electrons in. So we can use these d orbitals in hybridization. Let's see, 20, this is PF5. Phosphorus pentafluoride. Phosphorus has 5 valence electrons, fluorine is 7. 7 times 5 is 35, plus 5 from phosphorus is 40. So we have 40 valence electrons. Center element is phosphorus. 2, 3, 4, 5, 6, 7, 8. We know that we have 5 things bonded to our center element. So let's at least draw the line and attach a fluorine to it to show that. Then we have fluorine here, 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 and there. The line indicates that there is a bond consisting of 2 electrons between that phosphorus and that fluorine. This accounts for 10 electrons total. 2, 4, 6, 8, 10. We have 40 electrons starting out with. We've accounted for 10 already in that 5 coordinate system. We have 30 valence electrons left over. Nifty math. Fluorine wants 8, it sees 2, it needs 6. 2, 4, 6. 12, 18, 24, 30. So putting our remaining 30 valence electrons, completing the octets around each of our fluorines, completes the octets around each of our atoms. So if we look at phosphorus, its electron configuration is 3s, let me see, 3s2, 3s2, 3p2. No, 3p3, 3s2, 3p3. If we promote an electron up into the empty d orbitals, we get an sp D hybridization, an sp3d hybridization. So this S, all of the p, and one of the d orbitals have been hybridized to create 1, 2, 3, 4, 5 sp3d orbitals, and the remaining unhybridized 3d orbitals. That's what happens when phosphorus and fluorine react to form phosphorus pentafluoride. So the overlap that we see in phosphorus pentafluoride, we have fluorine here, fluorine there, fluorine there, fluorine there, and fluorine there. Each of these purple or blue colored shapes are the sp3 d orbitals. Since each orbital is identical to the other, they are degenerate, same energy level, but 5 atoms arranged around that center element. 2 are axial to one another, and 3 are equatorial to one another. If we have more electrons SF6, sulfur has 6 valence electrons, fluorine has 7, 7 times 6 is 42, total of 48 valence electrons. Since sulfur is your center atom, 1, 2, 3, 4, 5, 6, 7, 8, we know we have 6 things bonded to our center sulfur atom. So we need to draw the line, fluorine there, draw the line, and fluorine there. If we put the remaining electrons around, completing the octets around all the fluorines, we have consumed all the other available electrons. Sulfur's electron configuration, ground state electron configuration, 1s, 2s, 2p, 3s, 3p. Da, da, da. 3s, 3p, 3p4, 3p, 1, 2, 3, 4. Then the 3d orbitals. These are empty. There are 6 elements bonded to the center sulfur. Right now, we could only form bonds to 2 of those. But if we promote 1 electron from the p and 1 electron from the s up into the d orbital, so we promote this guy up to here and this guy up to here, we have 1, 2, 3, 4, 5, 6. So these become sp3d2 kinds of orbitals. So how can I predict what kind of hybridization I have on my center atom? One, draw the Lewis dot structure of the molecule. Count the number of lone pairs and the number of atoms bonded to your center atom. So the number of pairs plus the number of bonded atoms can tell us what the hybridization is. If the number of lone pairs and the number of bonded atoms is 2, we have an sp hybridized system. An example of this is beryllium chloride. If we draw the Lewis dot structure, how many electrons do we have? 4. Number of lone pairs plus number of bonded atoms. Any lone pairs? No. Bonded atoms? 2. 2. Hybridization of your center atom is sp. You have a combination of lone pairs and bonded atoms as 3. You have sp2 hybridization. The example here is boron trifluoride. Number of lone pairs plus the number of bonded atoms. No lone pairs on that center boron atom. 3, 1, 2, 3 atoms bonded to it. So this sum comes to 3. That boron is sp2 hybridized. Four center atoms, or excuse me, number of lone pairs plus the number of bonded atoms. If it comes to 4, you have sp3 hybridization. Methane. Any lone pairs on your carbon? No. 4 things bonded to it. Ammonia. How many atoms bonded to it? 3. How many lone pairs? 1. 3 and 1 is 4. Water. How many things are bonded to your center oxygen atom? 2. How many lone pairs? 2. 2 and 2 is 4. Center atom is sp3 hybridized. Five, number of lone pairs and bonded atoms. You have an sp3d hybridized system, PCl5. Last combination is 6. You have an sp3d2. An example of this is SF6. So here is a chart that you will have as part of your help sheets to help you understand and grasp on to what kind of hybridization you have in certain atoms in certain compounds. So this is just a summary of what was shown to you on the previous page. Again, you will have this chart to give you help on the exam. So determine the hybridization state of the center underlined atom in each of the following molecules. BeH2. Well, draw the Lewis dot structure. How many total valence electrons? 4 from beryllium, 2 from hydrogen. How many bonds does hydrogen form? 1. In our number of atoms bonded to our center atom and number of lone pairs on our center atom, any lone pairs on your beryllium? No. How many things are bonded to it? 2. So beryllium is, in beryllium hydride, sp hybridized. Aluminum triiodide, or aluminum iodide. Aluminum valence electron is 5. sorry. Valence electrons are 3 for aluminum. Valence electrons on iodine is 7, but we have 3 total. 3 times 7 is 21. 3 plus 21 is 24. We have a total of 6 electrons there. We have a total of 24 valence electrons. 24 minus 6 is 18. Iodine wants 8. It sees 2. It needs 6. 6, 12, 18. So are there any unpaired electrons on aluminum in the aluminum iodide Lewis dot structure? No. How many things are bonded to your center atom? 3 atoms. So your aluminum here is sp2 hybridized. PF3, 5 valence electrons. Fluorine is 7, but how many total of them do we have? 3. 7 times 3 is 21. 21 plus 5 is 26. Phosphorus, 1, 2. Let's start out with putting 8 around phosphorus. Let's start out by doing that. 18 left. Each fluorine wants the octet around it. So 6, 12, 18. So completing the octets around our fluorines, finish off the 18 electrons. How many lone pairs? 1. How many atoms are bonded to your center atom? 3. So that's 4. So this is an sp3 hybridized center phosphorus atom. This molecule is linear. This molecule mirrors that same molecular shape as boron trifluoride. And this molecule benefits from having, this molecule has the tetrahedral shape. So the orbital configuration with respect to beryllium and beryllium hydride is sp. Therefore, beryllium hydride is a linear molecule. When we look at aluminum iodide, it has a trigonoplanar shape. It is an sp2 hybridized orbital. It is a trigonoplanar molecular geometry. And then the PF3 is sp3. But one of the electrons completely fills one of the four sp3 hybridized orbitals, giving us only 3 empty orbitals to form a bond. So in phosphorus pentabromide, PBr3, phosphorus pentabromide, PBr5, valence electrons, 5 plus 7 for each bromine, but there are 5 of them. 7 times 5 is 35, total of 40 valence electrons. Well, let's start out again by putting the 8 electrons around phosphorus, but we know that there are 5 things bonded, so we have to have an extra electron pair drawn out. The line the line here represents the electron pair that goes to the bromine. Br, 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 Br. We've taken care of 2, 4, 6, 8, 10 valence electrons. We have 30 left. Again, this wants 8, it has 2, it needs 6. 6, 12, 18, 24, 30. So the remaining 30 valence electrons go around each bromine, completing its octet. So phosphorus here has no lone pair electrons, but it has 5 things bonded to it. So 5, it is an sp3d hybridized system. So there are 5 pairs of electrons around the phosphorus. There we conclude it is trigonobipyramidal. That we use phosphorus uses the sp3d hybridized orbitals. So phosphorus starts out as 1s2, 2s2, 2p6, 3s2, 3p3. Promotes an electron up from the s to get into the d. That gives us the 5 orbitals where we can pair with an electron from the bromine. We get sp3d type orbitals, and then 4 3d type orbitals that are not hybridized. So these hybrid orbitals overlap the p-type orbitals of bromine to form the 5 covalent phosphorus-bromine bonds. Because there are no lone pairs on the center phosphorus atom, the geometry of the phosphorus pentabromide is trigonobipyramidal. So if we look at carbon, carbon is a unique atom. Carbon is one of the only elements, it's not the only, but it's one of the only elements that is able to form more than one kind of bond. And is a unique feature of carbon. It's one of the only elements that has that ability. Therefore, that's why we have organic chemistry, because the chemistry of carbon that gives its unique properties. Therefore, it can form some fairly unique compounds. So again, let's look at what can happen with carbon. Ground state electron configuration. Carbon has 1s2, 2s2, 2p2. If we're going to have 4 bonds from the carbon, we have to promote an electron up from the 2s to get to the 2p. So if we have an sp2 hybridized carbon, 1s and 2 of the 3 p-type orbitals hybridize. 1 does not. Arbitrarily, we have chosen the pz. From an energy standpoint, we don't know which one it is. The p orbitals are identical. They are degenerate in their energy states. Therefore, we don't know if it's the pz. We are just arbitrarily designating it's the pz that is unhybridized. So we get 3 sp2 hybridized orbital. We're arbitrarily designating the z orbital, just simply because in the x, y, z orbital tricoordinate system, z is usually given the up-down orientation. X is right and left, y is front and back, z is up and down. Usually we designate z as the orbital that is not hybridized. That is just a convention that we use. We don't know which one is not hybridized. We're just choosing to represent it with the B. So if we look at a carbon atom is right here in the center, and the position of its orbitals, the sp2 hybridized are here in green. sp2, sp2, sp2. sp2. The one in gray is the unhybridized p orbital. Arbitrarily, we're designating it pz because it rests on this particular way that we've represented it, the z-axis. It could be any, but in this representation, we're choosing to use the z-axis. Bond angles between this orbital and this orbital is 120 degrees. Between here and here, 120 degrees. Between here and here, 120 degrees. This means that this orbital, and this orbital are all trigonoplanar with respect to one another. So this center carbon atom and these three green orbitals have a trigonoplanar arrangement. The position of the gray unhybridized p orbital is perpendicular. It's 90 degrees from the plane that contains the carbon atom and these three sp2 hybridized orbitals. It is 90 degrees between this plane and this unhybridized p orbital. So this gives us some unique bonding opportunities for this carbon atom. Where we see this kind of bonding is in the molecule known as ethylene, C2H4. If we just look at the hybridized orbitals that are in ethylene, we have the three sp2 hybridized orbitals. This carbon also has three sp hybridized orbitals. The bond that we designate between this carbon and this carbon, between this carbon here and that carbon there, is represented by that line, is represented by the overlap end-on of this orbital and that orbital. Notice what is not included in this diagram. It's the unhybridized pz orbitals. This representation shows the spatial proximal relationship of these two unhybridized p orbitals on each of your carbons. Again, we designate these as Z just simply because the tri-coordinate axis that we draw these things in, Z is up down. Could it be any of the p orbitals? Yes, we're just using Z as a familiar designation because of our tri-coordinate axis system. Notice that the pz orbital on this carbon is at 90 degrees to these guys. So these dotted lines and these bold lines represent these bonds. Sticking out basically above into the room and back out into the hallway are these unhybridized p atomic orbitals, right here on this carbon and on that carbon. Here they're not shown. Here they are. We can see that this dashed line represents this sp2 hydrogen bond. This bold line right here represents this sp2 hydrogen bond. This bold line represents this sp2 hydrogen bond. That dashed line represents that sp2 hydrogen bond. The p orbitals are sticking out above into the room and back out into the hallway. If we flip this like this to this, we can see those orbitals exist above and below the plane of the molecule that contains the carbons and these two hydrogen, this carbon and these two hydrogens. We can have two kinds of bonds. we have a single, what's called a sigma bond, which is the overlap of these sp2 hybridized carbon atoms. So the direct single bond between this carbon and this carbon is called a sigma bond. There is a second kind of overlap that forms a bond in ethylene. It is the bond that's formed between these two perpendicular p orbitals that are not hybridized, that exists above and below the plane of the molecule. We call these things pi bonds. So the resultant overlap between two hybridized orbitals end to end is called a sigma bond. Overlap of unhybridized orbitals side to side are known as pi bonds. So this carbon has, you can say each of these carbons has 3 sigma bonds. Sigma bond here, sigma bond there, sigma bond there. Sigma bond here, sigma bond there, sigma bond there. And this carbon has 1 pi bond. 1, 2, 3 sigma, 1 pi. 1, 2, 3 sigma, 1 pi. That carbon is looked at as being bonded to 4 things. It's bonded to 2 different things and bonded to the same thing twice. So it's got these 2 hydrogens, and this carbon is bonded to that carbon twice to give you 1, 2, 3, 4 bonds. The same thing that can be said for this carbon. It's bonded to 1, 2, 3 things, 4 via the pi bond. This is a covalent bond, and the pi bonds are covalent bonds. The bonding here is direct and on between the sp orbitals, these hybridized sp2 orbitals. But the bonding here in the pi bond are from unhybridized p atomic orbitals. That pi bond is still considered a covalent bond, but it is different than the sigma bond. The sigma bond is hybridized end-on interaction. The pi bond is side-to-side unhybridized orbital interaction. So we can see the 3 sigma bonds and the pi bonds, giving each carbon 4 bonds. The sigma bonds are between and on overlap of the hybridized orbitals, and the pi bonds are from side to side overlap of the unhybridized p atomic orbitals. We can look at ethylene in a different way. Carbon-carbon bond is your sigma bond. Carbon-hydrogen sigma, carbon-hydrogen pi bond. Carbon-carbon sigma, carbon-hydrogen sigma, carbon-hydrogen sigma, pi bond. This image is on figure 10.7 in your figure 1017 in the text. It shows the planar nature of the ethylene molecule. All of the sigma bonds exist in the blue sigma, in that blue plane. These are all single sigma bonds. The 4th bond between each of your carbon atoms exists in the overlap between the 2 unhybridized p atomic orbitals on each carbon, thus known as the pi bonds. The sigma and the pi bonds are 2 very different kinds of bonds. The bond strength of the carbon-carbon pi bond is 620 kilojoules per mole, and that of the carbon-carbon single bond is 347 kilojoules per mole. So if we look at the electron distribution about this molecule, we can see that above and below the center part of the molecule, we have higher centers of electron density, meaning that we have the electrons of the single bond, but also the electrons of the double bond focused in the center area of this molecule, the area between the two carbon atoms. We can have other kinds of hybridization. We've shown you sp3. We've shown you sp2. Carbon can even have sp hybridization. sp3 is your tetravalent. Every carbon that has sp3 hybridization is bonded to 4 different things. sp is all single bonds, but an sp2 carbon involves a double bond. A carbon in a double bond is bonded to 3 things, but one of those 3 things it's bonded to twice to make the 4th bond. What happens when we have an sp hybridized carbon? Well, we've talked about single bonds, which is sp3. We talk about double bonds, which is sp2. Then if we go to sp, we need to be talking about, or we are talking about, triple bonds. The molecule that we can look at that shows this is what we call acetylene. Here's the ground state of carbon. We promote the electron from the 1s into the 2p. But we only mix an s and a p-type orbital. So we have sp hybridized orbitals and 2 unhybridized p-atomic orbitals. Here designated the py and the pz. Again, they could be any, but for the use of our xyz coordinate system, we designate these as y and z. So here are our unhybridized orbitals, py and pz. If we take a look at the molecule of acetylene, it is a carbon-carbon triple bond. We have an sp hybridized bond between the carbon here and this hydrogen, and we have an sp hybridized bond between this carbon and that hydrogen. But remember, on each carbon there is also a bond between the carbons. So in this, we have shown to you correctly where each of the hybridized orbital bonds are. But remember, we still have other unhybridized orbitals that we need to take into account. They are the the pz and the py. So the pz are up, down. The py are front and back. So sp, 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 sigma bond, sigma bond, sigma bond. This only has the hybridized orbitals. When we bring in all the other unremaining hybridized orbitals that exist above and below and in front and back, we can see that they have this side-to-side overlap, such that we have 2 pi bonds. 1 pi bond between the pz and 1 pi bond between the py orbitals. So if you want to do this, we'll call this the pi z, if we can use that designation, pi z, and these are the pi bonds from the y orbitals. So we have the sigma bonding in blue and the pi bonding in yellow. This is the bonding that we have in acetylene. Acetylene is a linear molecule. So a sigma bond is a single bond. It can be sp, sp2, or sp3 hybridized. A single bond in a compound is a sigma covalent kind of bond. If we have a double bond, we have one sigma and one pi bond. If we have a triple bond, we have one sigma bond and two pi bonds. So we're about at the edge of time for the lecture that we have, for the time that we have for this lecture. Hope you enjoyed this video. Hopefully we'll straighten some things out and answer some questions. I will pick up at this slide, slide 42, for our lecture on Wednesday of next week. Have a good weekend. I will see you Tuesday, 12:30, or Tuesday at 6 p.m. in Miller Hall, room 221. Have a good weekend. I'll see you on Tuesday.